Page 142. Most of chapter 2 we're not going to do. I don't think so for the next couple days. All right, we're going to know and use the segment addition postulate. Good news is you already know it, and you've already used it. We're going to know and use the reflexive, symmetric, and transitive properties of segment congruence, which you've already used those properties when you solve equations. You've just used those properties as properties of equality. Now we're going to use them as properties of congruence. All right, the segment addition postulate is at the bottom of 142. It says, first of all, it says, we've already learned about what it means for a point to be between two other points. Remember, it's got to be on the same line as the other 2 points. For one point to be between two others, the 3 points have to be collinear. Okay? And this relationship can be expressed as the segment addition postulate. So here it is. If A, B, and C are collinear, then point B is between A and C if and only if the length of AB plus the length of BC equals the length of AC. Now, let's just look at this as simply as we can. If we know that's a line, all right, if we're given this and we know that that's a line segment, doesn't it have to be true that the length of that segment plus the length of that segment equals the length of the entire segment? It's just got to be. And we've already used that, haven't we? Okay, it's got to work that way. That's why this one's called a postulate. In mathematics, a postulate, and they used to be called axioms, but that word's become out of use, basically, and it's replaced with postulate. A postulate in math is something that is accepted as true without proof. Okay? Now, we're going to have a lot of postulates, because we're high school students, that can actually be proven. All right? When we prove them, we call them theorems. When we just use them without proof, we call them postulates. This one can be proven. It just takes a little more advanced math than what we're capable of right now. Okay? So it's a postulate, and postulates are supposed to be, quote unquote, obvious. Obvious in math doesn't always mean obvious. Hopefully it means that if somebody explains it to you, it'll make sense. All right, but this one kind of is obvious, isn't it? It's got to work that way. Now, I also want to talk about this phrase here, if and only if. We're going to run into that. All right? And what that is that's called a biconditional. Whenever you have the phrase if and only if in a sentence, that makes the sentence a biconditional. Now, this won't be on the test, this kind of stuff, but stuff you ought to know, because I'm going to use these terms, okay? And what it means is, first, you read the sentence the way it's written. If A, B, and C are collinear, and point B is between A and C, and the if and only if is replaced with then AB plus BC equals AC. Then you can also read the sentence in the other order. Okay? That's called the converse. When you change the order of an if-then statement, you get its converse. Converses are sometimes true, not always true. I'll give you an example in a minute. Okay? But when you see if and only if, that means the statement read in one order and the statement read in the other order are both true. So this one statement that's in our postulate also means if the length of AB plus the length of BC equals AC, then A, B, and C are collinear, and point B is between A and C. Okay, so it works either way. You with me? All right, let's see if I can make up an example of when a converse wouldn't be true. And of course, I can't think of one off the top of my head. If a figure is a square, then it has 4 sides. True? Its converse would be, if it has 4 sides, then a figure is a square. False. So see, the statement was true, but its converse was false. Lots of times the converse seems reasonable at first, even when it's false. Because if you didn't think about that a little bit, you'd say, well, that's true. No, it wasn't either, was it? Okay? All right, so segment addition postulate. Got it? Let's see. These are from page 19. We've done these before. Let's do number 21 here. It says, find the value of the variable and the length of yz if y is between x and z. Remember how we did these? We draw it. We put x and z at the end points. We put y somewhere in here between. And then we label what they give us. And this is part of your assignment, even though I didn't have it written on the assignment list. The length of xy is 11. The length of yz is 4c. And the length of xz is 83. We use the segment addition postulate to set up our equation. The segment addition postulate applied to this drawing would be, the conclusion would be that the length of xy plus the length of yz equals the length of xz. Now, you don't have to write this part, but here's the conclusion of what the segment addition postulate would say. Isn't it? So let's put in the expressions they give us. So the length of xy, 11, plus the length of yz, 4c, equals the length of xz, 83. And then we solve it for c. So we subtract 11 from both sides. What's 83 minus 11? And then we divide both sides by 4. And what's 72 divided by 4? And we have C. All right, so we've used the segment addition postulate here. Now, they tell us to also find the length of YZ. The length of YZ is 4C. Well, 4 times 18 better give us that 72 again, hadn't it? And there we go. All right, so you remember doing these? We were using the segment addition postulate. I think I probably even said something like, now, later on, we'll call this the segment addition postulate. Well, now we call this the segment addition postulate. All right, 22.
Do we have to do the YT thing?
They asked us to. All right, 22, let's draw it. We have segment XZ and Y is between them. The length of XY is 6B. The length of YZ is 8B. And the length of XZ is 175. So according to the segment addition postulate, since Y is between X and Z, then the length of XY, 6B, plus the length of YZ, 8B, equals the length of XZ, 175. All right, 6B plus 8B. And what's 175 divided by 14? 12.5. And then the last thing, find the length of YZ. All right, YZ was 8B. So what is 8 times 12.5? It's 100. All right, let's do 23. All right, on 23, let's draw it. X, Z, Y is in here. Let's label it. The length of XY is 7a. The length of YZ is 5a. And the length of XZ is 6a plus 24. All right, write down the equation. Did you get the same equation I did? All right, solve it. Did you get the same A I got? All right, then the length of YZ would be 5a, well, 5 times 4, and that's 20. All right, you think you got the hang of them? All right, so let's work some that you haven't worked before. I got these from page 44. Do these two and see how it goes. In both cases, I used the segment addition postulate to get my equation, didn't I? According to the segment addition postulate, since S is between R and T, the length of RS plus the length of ST must equal the length of RT. Remember this? You've heard me say this a bunch of times. Sometimes we add things together because we know what the result is. We add the length of RS and the length of ST because we know what the result is. Sometimes we know it as a number, like in these two. Sometimes we know it as an expression, like we did there in 23. But in all these cases, by using the segment addition postulate, you can add together the lengths of the smaller segments because you know the result is the length of the whole segment. Think you got it? I think you got it. All right. Just in case, try these two. These are from page 45. You know what I thought was the toughest part of these? The decimal didn't bother me. I thought the toughest part of these was making sure I found the correct one. I almost found the length for number 4, I was going to find the length of BC without thinking about it. So I had to look back at the directions to make sure I found the right one. I'm not going to trick you. At least I'm not going to try to trick you on any quiz. Bless you. So what do you think? All this ringing a bell? Any questions on either of these, 4 or 5? Okay. I don't think we need any more. Back to page 143. Nope. Where is this? Where did I get these from? I got these from page 134. Now, these are properties that you use with equations all the time. The addition property of equality is the property that allows you to add a number to both sides of an equation. Subtraction property allows you to subtract a number from both sides of an equation. Multiplication property, division, all right? Now, these 3, though, let's talk about. The reflexive property of equality is really, really simple. It says that any number is equal to itself. Well, of course a number is equal to itself. Every time we talk about the number 5, we mean 5. There's never a day when we say 5 and 5 actually means 32, right? It never happens. A number is always equal to itself. The symmetric property, and people get symmetric and reflexive confused because both of them are so intuitive. You understand them even if nobody ever points them out to you, okay? And it's this: if A equals B, then B equals A. How about like this? If I work out an equation and I get X equals 5, and you work out the same equation and you get 5 equals X, don't you expect me to count yours correct? Yes. And why would you expect me to count yours correct? Because it's the same thing. That's what the symmetric property says. X equals 5 and 5 equals X are the same thing. Okay? So try to keep those 2 straight. Reflexive, symmetric. You're going to be frustrated with yourself when you miss a test question because you get those 2 confused. So keep them straight. Intransitive, if A equals B and B equals C, then A equals C. All right? If David's age equals Cam's age, and Cam's age equals Ben's age, wouldn't we all conclude that David's age equals Ben's age? That's the transitive property. Okay? All right. Substitution, we're going to use a lot, and we used it today already, didn't we? When we went back and found the length of AC or YZ or whichever one it was, didn't we substitute a number in for X? The substitution property says if A equals B, then A may be replaced by B in any equation or expression. It also means that B can be replaced by A. All right? So, in other words, once you know 2 things are equal, one can replace the other anytime you want. Once you know that X equals 5, you can replace the X with 5. You could also replace a 5 with X. Now, do we want to do that very often? No, but we could. According to the substitution property, that's a mathematically valid thing to do. It may not be very useful, but it's something we can do. So that's substitution, and you've done that for years too, haven't you? You found X, and then you put whatever number that is back in for X to evaluate your expression. Now, we're calling them measures of angles, lengths of segments, instead of just saying evaluate the expression. But that's what it is. Okay? And then distributive, we know that. So all those properties seem familiar to you? All right. Now we're on page 143. I'm sorry I'm jumping around everywhere, but there was just a lot of territory. We did not need to cover each section. We just needed to talk about one thing out of it. And we have these properties of reflexive, symmetric, and transitive for congruent segments, or, as the book says, of segment congruence. All right, so since segments with the same measure are congruent, congruence of segments is also reflexive, symmetric, and transitive. Okay? Because we know that these properties are true for numbers, right? That's what we just went over. Now we're going to show that they're true. We're going to learn that they're true for segments themselves, not just lengths of segments. Okay? Now let me back up a second. Since we know these properties are true for numbers, isn't the length of a segment a number? So then we know that these properties are true for lengths of segments. Aren't measures of angles numbers? So these properties are also true for measures of angles. Okay? What we've not said yet is that these properties are true for segments themselves and angles themselves. And to be correct mathematically, you have to say that they apply to something before you apply them. Okay? So here we are saying, hey, they apply to segments. I mean, doesn't it make sense that segment AB is congruent to segment AB? How else could it work, right? I mean, the segment's got to be the same as itself. So segment AB has got to be congruent to segment AB. That's reflexive. Symmetric. If segment AB is congruent to segment CD, it's only fair to say that segment CD is congruent to segment AB. And again, if we were doing a proof in a few weeks, and at the end of my proof, I said that, and at the end of your proof, you said that, you want yours counted correct, don't you? Symmetric property says so. Okay? Now, we'll also learn, though, that in a proof, you'll actually have to use that symmetric property to turn it in what you were trying to prove. You can't get close in a proof. You got to get exactly it. So even though we know that's exactly that, we would then have to take a step to point out, hey, that's exactly that. We'll get there. All right, so reflexive symmetric makes sense, right? Transitive makes sense for congruent segments as well. I mean, think about it. It has to work this way. If that segment's congruent to that one, and then CD is congruent to EF, doesn't the one we started with have to be congruent to the one we ended with? It's got to work that way. Okay? All right. Questions? Here's your assignment. On page 147, do number 17, do 23 through 26, and 34 through 46.
46.
What did I say, 46? I meant 36.